Hi everyone. Have you ever wondered why your phone heats up during gaming and charging? Proper heat removal is essential to ensure device function well and last longer. During cooling, heat passes through several interfaces. We know that engineering surfaces are never perfectly smooth. They have irregularities that creates resistance to heat flow at interfaces, leading to a temperature jump at the interface. This phenomena is known as thermal contact conductance or TCC. TCC is influenced by factors such as surface roughness, applied pressure, material properties, and interface materials. Over the years, several analytical, experimental, and numerical models have been proposed to predict TCC at the interfaces. So, experimental models are based on ASTM D5470 standards. It's using a one-dimensional heat transfer approximation, where TCC at the interface is expressed as H equal to Q by A delta T. These models typically assume a constant TCC value at the interface, but in reality, TCC varies in plane due to non-uniform pressure distribution. Our aim is to address this gap in the literature. The study focused on three applications where in-plane variation of TCC is critical for accurate estimation. The first and third studies uses inverse heat transfer techniques to estimate TCC. Unlike usual simulations where the cause is known and the effect is predicted, inverse heat transfer places temperature sensors in sensitive locations to record the effect, that is temperature. This data combined with optimization techniques helps back predicting the cause, either here TCC, by minimizing the difference between experimental and simulated temperature. Study 1 focused on heat transfer in spacecraft bolted joints. The contact area is measured using Fujifilm pressure-sensitive films and incorporated into computational models. The study explores various bolt-outs and arrangements and is extended to anisotropic materials such as honeycombs. The second study is purely experimental and focused on ALSIC metal matrix composites. In electronic package mountings, difference in thermal expansion coefficient between the heatsink and the package material can cause detachment, leading to system failure. By adjusting the SiC content in the composites, the thermal expansion coefficient can be tailored, making this material ideal for uses in the heatsink applications. The third study focused on heat transfer in metal forms and also employs inverse heat transfer techniques. As shown in the figure, actual contact pressure data measured using pressure-sensitive films is incorporated into the computational model. This helps estimate the in-plane variation of TCC. As shown in the figure, the contact area is measured for different tops, and the computational domain is divided into three regions with the TCC values H1, H2, and H3. Using experimental boundary conditions and optimization techniques, these values are estimated. H1 is located directly under the bolt head, H2 corresponding to the contact area, and H3 covers the remaining area. The result shows that H1 greater than H2 greater than H3. In the second study, semi-majors reveals SiC particles at the interface, contributing to non-uniform TCC. An empirical correlations for TCC was developed based on the percentage of SiC, surface roughness, and applied pressure. The experimental data shown in the figure uses red points to represent different combinations of these parameters. A regression model for TCC was derived, and the trends of TCC with respect to each of these factors are illustrated. In the third study, semi-majors were taken to characterize copper and aluminum metal forms with different pores per inches. For each cases, the actual contact pressure distribution was measured using pressure-sensitive films as shown in the figure. Experiments were conducted to get the temperatures, and the in-plane variation of TCC at the interface were determined by using inverse heat transfer techniques. All the studies were conducted under simulated outer space conditions. For further in-depth details, please refer to the providing publications.